Welcome to the deep dive. You sent in a really interesting set of materials this time around, and it's all about mathematical induction.
Yeah.
Yeah, so we're going to take a deep dive into it today.
Okay.
It's a pretty powerful proof technique.
It is.
And yeah, we're going to unpack not just like the how-to, but like the why behind it.
I think that's a great way to approach it.
Yeah.
Yeah.
So you're going to come away from this deep dive understanding it a lot better.
I think so.
All right, so let's jump right in. One of the sources you shared starts by setting the stage with deductive reasoning. It uses that classic Socrates example, like Socrates is a man,
Right.
all men are mortal,
Right.
therefore Socrates is mortal. You know,
Yeah.
for us non-philosophers,
Yeah.
what is the core principle at play here?
Well, the Socrates example is a perfect illustration of deduction.
Yeah,
The key is that if those initial statements,
right.
that Socrates is a man and all men are mortal,
Yeah.
if those are true,
Mm-hmm.
then the conclusion that Socrates must be mortal.
Is absolutely guaranteed.
Okay.
Deductive reasoning takes a general rule and applies it to a specific case.
Okay.
Your material also gave a nice mathematical example.
Okay.
8 is divisible by 2.
Okay.
Any number divisible by 2 is even. Therefore, 8 is even.
Yeah.
It's the same logical structure.
Okay, so general rule applied to a specific instance
Exactly.
leads to a certain conclusion.
Yeah.
Okay, now how does mathematical induction fit into this picture?
Uh-huh.
Because my understanding from the sources is that, general inductive reasoning
Mm-hmm.
involves like looking at specific observations,
Right.
and then you're kind of trying to come up with a general rule based on those observations.
Exactly.
And that's how a lot of like science is done.
Right.
Like coming up with hypotheses.
Yeah. General inductive reasoning moves in the opposite direction from deduction.
Okay.
It's about observing patterns in specific cases
Yeah.
and then formulating a broader hypothesis or rule based on those observations.
So think of observing many sunsets
Uh-huh.
and noticing the sky turns red each time,
Yeah.
leading to a hypothesis about sunsets and red skies.
Okay, so like if I notice that like the first few odd numbers,
Right.
like 1, 3, 5, 7,
Yeah.
seem to be prime numbers
Oh.
using general induction,
Uh-huh.
I might make the guess that all odd numbers are prime.
Yeah.
But, my sources also emphasize that this kind of guess isn't a foolproof proof.
Exactly.
Right, we could easily find a counterexample like 9.
Exactly. General induction is fantastic for forming ideas
Yeah.
and spotting potential truth,
Yeah.
but it doesn't give us the absolute certainty of a mathematical proof.
Right.
That's where the principle of mathematical induction comes in.
Okay.
And it's specifically designed for proving statements about positive integers with that absolute certainty.
Okay, so this principle of mathematical induction is our focus for today.
It is.
And the material you shared highlights that it's particularly useful for statements involving natural numbers, 1, 2, 3, and so on.
Yeah.
Now, to really wrap our heads around this,
Uh-huh.
one of the sources used a brilliant analogy,
Yeah.
a line of falling dominoes.
Uh-huh.
How does that image
Yeah.
help us understand the core idea of mathematical induction?
The domino analogy is incredibly insightful.
Okay.
Imagine you have a long, potentially infinite line of dominoes,
Yeah.
all standing upright,
Mm-hmm.
and close enough that if one falls, it will knock over the next one.
Yeah.
Mathematical induction says that if we can guarantee two things,
Uh-huh.
then all the dominoes will fall.
Okay.
First, we need to make sure the very first domino gets pushed over.
Okay.
Second, we need to ensure that if any domino falls,
Uh-huh.
it will definitely knock over the one right after it.
Right, I can visualize that. So you give the first push
Yeah.
to start the chain reaction.
Exactly.
And each falling domino triggers the next one.
Yep.
So how do these two conditions in the domino analogy
Yeah.
translate into the actual steps of a mathematical induction proof?
The two domino conditions map directly to the two essential steps.
Okay.
The first condition,
Uh-huh.
the first domino falling,
Yeah.
corresponds to the basic step
Okay.
in mathematical terms.
Uh-huh.
This means we need to show that the statement we want to prove,
Right.
let's call it P of n,
Okay.
is true for the first relevant natural number.
Right.
Usually this is n equals 1.
Uh-huh.
However, as your material correctly points out,
Yeah.
sometimes a statement might only hold for n greater than or equal to, say, 4.
Right.
In that case, our basic step would start by proving P of 4 is true.
Right.
It's about establishing that initial domino has fallen.
Okay, got it. That sets the whole thing in motion.
Exactly.
And the second condition,
Yeah.
where each falling domino knocks over the next.
That's the inductive step.
Okay.
Here we assume that our statement P of n
Uh-huh.
is true for some arbitrary positive integer k.
Okay.
This assumption
Yeah.
that P of k is true is what we call our inductive hypothesis.
Okay.
Our goal in this inductive step
Uh-huh.
is then to use this assumption
Okay.
to prove that the very next statement in the sequence, P of k plus 1,
Right.
must also be true.
Okay.
We're essentially showing that if the k domino falls,
Uh-huh.
P of k is true,
Right.
it's guaranteed to knock over the k plus 1th domino.
Yeah.
P of k plus 1 is true.
So if we can show that P of 1 is true,
Exactly.
the first domino falls,
Yeah.
and that the truth of P of k always leads to the truth of P of k plus 1,
Exactly.
each falling domino knocks over the next one,
Yeah.
then we've created an unstoppable chain reaction.
Precisely.
And that proves that P of n must be true for all natural numbers n.
Yes.
Starting from our base case. It's like
Yes.
we give the first domino a push,
Yeah.
and the setup ensures that every single one after it will fall.
Exactly.
Okay.
And your sources even touch upon a deep property of the natural numbers that makes this work. They mention that the set of natural numbers is the smallest inductive set. Think of it this way.
Okay.
An inductive set is any set of numbers that contains 1.
Yeah.
And if it contains any number x,
Uh-huh.
it must also contain x plus 1.
Okay.
The natural numbers are the smallest such set,
Yeah.
meaning any other set with this inductive property must contain all the natural numbers.
Okay.
This fundamental property
Right.
is the bedrock upon which the validity of mathematical induction rests.
Okay.
It guarantees that if our domino effect starts,
Yeah.
it covers all the natural numbers.
That's a really powerful insight into why this method is so sound.
Yeah.
Now, one of the classic problems that your material brings up is finding a formula for the sum of the first n positive integers.
Right.
So like 1 plus 2 plus 3 plus ... plus n.
Yeah.
And it mentions this conjectured formula, n times n plus 1 over 2.
Yeah.
And we can like check this for a few small numbers. Like if n equals 4, sum is 10, and then 4 times 4 plus 1 over 2 is also 10.
Yes.
But just checking a few examples isn't a proof that it works for every n.
That's right.
Right. We need that guaranteed chain reaction.
Exactly. Testing a few cases can give us strong evidence that a formula might be correct. But mathematical induction provides the rigorous proof that leaves no doubt.
Right.
It establishes that if the formula holds for some number k,
Yeah.
it absolutely must hold for k plus 1,
Right.
creating that infinite chain of truth
Yes.
that starts with the base case, usually n equals 1.
Okay, so we've got the principle down.
Yep.
Now let's see how this works in practice
Okay.
with some of the examples from your material. The first one is proving the formula for the sum of the squares of the first n natural numbers.
All right.
So that's 1 squared plus 2 squared plus 3 squared plus ... plus n squared equals n times n plus 1 times 2, n plus 1 all over 6.
Okay.
Can you walk us through the basic step and the inductive step for this one? Certainly. So let P of n be the statement 1 squared plus 2 squared plus ... plus n squared equals n times n plus 1 times 2n plus 1 over 6.
Okay.
First, the basic step.
Uh-huh.
We need to show that P of 1 is true
Okay.
when n equals 1.
Yeah.
The left side of the equation is just 1 squared.
Uh-huh.
The right side is 1 times 1 plus 1 times 2 times 1 plus 1 all over 6,
Okay.
which is 1 times 2 times 3 over 6, which is 6 over 6, which is 1 since 1 squared equals 1.
Yeah.
We've shown that P of 1 is indeed true.
Right.
The first domino has fallen.
Okay.
Now for the inductive step,
Yeah.
we assume that P of k is true for some positive integer k.
Okay.
This is our inductive hypothesis. 1 squared plus 2 squared plus ... plus k squared equals k times k plus 1 times 2k plus 1 over 6.
Okay.
Our goal now is to use this assumption
Yeah.
to prove that P of k plus 1 is also true.
Meaning we want to show that 1 squared plus 2 squared plus ... plus k squared plus k plus 1 squared equals k plus 1 times k plus 1 plus 1 times 2 times k plus 1 plus 1 all over 6.
Okay.
Which simplifies to k plus 1 times k plus 2 times 2k plus 3 all over 6.
Okay, I'm with you. So we're saying, okay, we're just accepting that our formula works for some number k.
That's right.
And now our goal is to show it must work for the next number k plus 1.
Exactly.
Okay.
So we begin with the left side of the p of k plus 1 equation, 1 squared plus 2 squared plus ... plus k squared plus k plus 1 squared.
Yeah.
Because of our inductive hypothesis, We know that the sum of the first k squares
Right.
is equal to k times k plus 1 times 2k plus 1 over 6.
Right.
So we can substitute that in k
Right.
times k plus 1 times 2k plus 1 over 6 plus k plus 1 squared.
Right.
Now, the challenge is to manipulate this expression algebraically until it looks exactly like the right side of p of k plus 1,
Right.
which is k plus 1 times k plus 2 times 2k plus 3 all over 6.
Wait, so this is where we put on our algebra hats.
Exactly.
It looks like we're going to need to combine those terms,
Yep.
probably by finding a common denominator.
Precisely. The common denominator here is 6.
Okay.
So we rewrite the second term with a denominator of 6.
Okay.
So we get open square bracket, k times k plus 1 times 2k plus 1 plus 6 times k plus 1 squared, close square bracket, all over 6.
Okay.
Now notice that k plus 1 is a common factor in both parts of the numerator. Let's factor it out.
Okay.
So we have k plus 1, open square bracket, k times 2k plus 1 plus 6 times k plus 1, close square bracket, all over 6.
Okay.
Next, we expand the terms inside the square brackets.
All right.
K plus 1, open square bracket, 2k squared plus k plus 6k plus 6, close square bracket, all over 6. Then we combine the terms within the brackets.
Okay.
K plus 1, open square bracket, 2k squared plus 7k plus 6, close square bracket, all over 6.
Okay.
Finally, we need to factor the quadratic expression 2k squared plus 7k plus 6.
Right.
This factors into k plus 2 times 2k plus 3.
Ah, I see it. So we end up with k plus 1 times k plus 2 times 2k plus 3 all over 6.
Exactly.
Which is exactly the formula that we wanted for p of k plus 1.
Precisely.
The dominoes are falling.
Exactly, because we've shown that if the formula holds for k,
Yeah.
it must hold for k plus 1. And we've confirmed it holds for the base case of n equals 1.
Right.
The principle of mathematical induction tells us this formula for the sum of the first n squares
Yeah.
is true for all positive integers n.
That was a great demonstration.
Thank you.
Okay, so let's move on to another example.
Right.
Proving the inequality 2 to the n is greater than n
Yep.
for all positive integers n.
Yeah.
This is a different flavor of statement because we're dealing with greater than rather than equals.
Right. The fundamental structure of the inductive proof remains the same.
Okay.
Let p of n be the statement. 2 to the n is greater than n.
Okay.
Basic step. We check if p of 1 is true
Okay.
for n equals 1.
Yeah.
2 to the 1 is 2.
Uh-huh.
And 2 is indeed greater than 1.
Right.
So p of 1 holds inductive step. We assume p of k is true for some positive integer k.
Yeah.
Meaning 2 to the k is greater than k. Our goal is to show that p of k plus 1 is also true.
Okay.
Which is 2 to the k plus 1 is greater than k plus 1.
Right.
So starting with our inductive hypothesis,
Yeah.
2 to the k is greater than k. A natural first step to get to 2 to the k plus 1
Okay.
is to multiply both sides of the inequality by 2.
Okay.
Since 2 is a positive number,
Yeah.
the direction of the inequality doesn't change.
Right.
So 2 times 2 to the k is greater than 2 times k. So 2 to the k plus 1 is greater than 2k.
Right.
Now, we need to somehow bridge the gap between 2k and k plus 1. We want to show that 2k is greater than or equal to k plus 1
Right.
for all k greater than or equal to 1.
How do we establish that 2k is always at least k plus 1?
We can look at their difference.
Okay.
Consider 2k minus open parenthesis k plus 1 close parenthesis,
Okay.
which simplifies to k minus 1
Right.
for all positive integers k.
Yeah.
That is k greater than or equal to 1.
Oh.
K minus 1 is greater than or equal to 0.
Right.
This means k greater than or equal to 1 implies 2k minus open parenthesis. K plus 1 close parenthesis is greater than or equal to 0, which in turn means 2k is greater than or equal to k plus 1.
Okay.
Since we've established that 2 to the k plus 1 is greater than 2k,
Yeah.
and that 2k is greater than or equal to k plus 1, we can conclude that 2 to the k plus 1 is greater than k plus 1. Therefore,
Right.
p of k plus 1 is true whenever p of k is true.
Okay.
By the principle of mathematical induction,
Yeah.
the inequality 2 to the n is greater than n, and it holds for all positive integers.
Okay.
Notice here how the strategy in the inductive step was to manipulate the hypothesis to get a related form
Yeah.
and then use another inequality to reach our goal.
That makes perfect sense. So we use our assumption to kind of get part of the way there.
Exactly.
And then we use a bit of algebra to connect it to that next step in the sequence.
Yep.
Okay, let's try example 3.
Okay.
Proving the formula for the sum of a series of fractions.
All right.
This one looks a little intimidating.
Yeah, it can look that way.
So 1 times 2 plus 1 over 2 times 3 plus 1 over 3 3 times 4 plus,
That.
plus 1 over n times n plus 1
Yeah.
equals n over n plus 1.
Okay.
Done.
So the P of n be the statement 1 over 1 times 2 plus 1 over 2 times 3 plus ... plus 1 over n times n plus 1 equals n over n plus 1.
Okay.
Basic step.
Uh-huh.
We check for n equals 1.
Okay.
The left side is just the first term, 1 over 1 times 2,
Uh-huh.
which is 1/2. The right side is 1 over 1 plus 1, which is 1/2.
Okay.
Since both sides are equal,
Yeah.
P of 1 is true.
Okay.
Inductive step.
Uh-huh.
We assume P of k is true.
Okay.
1 over 1 times 2 plus 1 over 2 times 3 plus ... plus 1 over k times k plus 1 equals k over k plus 1.
Right.
We need to prove P of k plus 1.
Okay.
1 over 1 times 2 plus 1 over 2 times 3 plus ... plus 1 over k times k plus 1 plus 1 over k plus 1 times k plus 2
Yeah.
equals k plus 1 over k plus 2.
Right.
Starting with the left side of P of k plus 1
Uh-huh.
and using our inductive hypothesis,
Yeah.
we can replace the sum of the first k terms.
Okay.
So k over k plus 1 of k plus 1 times k plus 2.
Right.
To add these two fractions,
Uh-huh.
we need a common denominator,
Yeah.
which is k plus 1 times k plus 2.
Okay.
Open square bracket k times k plus 2 plus 1 close square bracket.
Uh-huh.
All over open square bracket, k plus 1 times k plus 2 close square bracket.
Oh, it's...
Now we expand the numerator.
Right.
Open parenthesis k squared plus 2k plus 1 close parenthesis.
Okay.
All over open square bracket k plus 1 times k plus 2 close square bracket.
Uh-huh.
Notice that the numerator is a perfect square.
Yeah, k plus 1 squared.
Exactly.
Okay.
So we have open parenthesis k plus 1 close parenthesis squared.
Yeah.
All over open square bracket k plus 1 times k plus 2 close square bracket.
Mm-hmm.
Since k is a positive integer,
Yeah.
k plus 1 is not 0.
Right.
So we can cancel out one k plus 1 term from the numerator and the denominator.
Okay.
And we're left with k plus 1 over k plus 2.
Right.
This is exactly the right side of P of k plus 1.
It is.
Therefore, by mathematical induction,
Uh-huh.
the formula holds for all n greater than or equal to 1.
Okay.
Again, the strategy here was to use the inductive hypothesis to substitute
Yeah.
and then manipulate the resulting expression to match the form we wanted for the next step.
I like this. So use the hypothesis to substitute.
Yeah.
And then algebra. Okay, we're making great progress.
We are.
The next example involves divisibility,
Okay.
proving that 7 to the n minus 3 to the n is divisible by 4 for every positive integer n.
All right.
So how do we approach a divisibility proof using induction?
So let P of n be the statement.
Okay.
7 to the n minus 3 to the n is divisible by 4.
Okay.
Remember,
Yeah.
divisible by 4 means that 7 to the n minus 3 to the n can be written as 4 multiplied by some integer.
Right. Okay.
Basic step.
Uh-huh.
We check for n equals 1.
Okay.
7 to the 1 minus 3 to the 1 equals 4.
Right.
And 4 is clearly divisible by 4.
Right.
4 equals 4 times 1.
Yeah.
So P of 1 is true.
Right.
Inductive step.
Uh-huh.
We assume P of k is true for some positive integer k,
Okay.
which means 7 to the k minus 3 to the k is divisible by 4.
Right.
So we can write 7 to the k minus 3 to the k equals 4d for some integer d.
Right.
Our goal is to show that P of k plus 1 is also true.
Meaning 7 to the k plus 1 minus 3 to the k plus 1 is divisible by 4.
Okay.
Let's look at the expression 7 to the k plus 1 minus 3 to the k plus 1
Okay.
and try to relate it to our inductive hypothesis.
Okay.
7 to the k plus 1 minus 3 to the k plus 1 equals 7 times 7 to the k minus 3 times 3 to the k. The key strategy here
Yeah.
is to manipulate this expression so that we can isolate the term 7 to the k minus 3 to the k,
Okay.
which we know is a multiple of 4
Right.
from our inductive hypothesis.
Yeah.
We can rewrite 7 times 7 to the k in a clever way.
Okay.
7 times 7 to the k equals 7 times open parenthesis, 7 to the k minus 3 to the k plus 3 to the k close parenthesis,
Okay.
which equals 7 times open parenthesis, 7 to the k minus 3 to the k close parenthesis plus 7 times 3 to the k.
Okay.
Notice how we've introduced the 7 to the k minus 3 to the k term?
Now substitute this back into our expression for 7 to the k plus 1 minus 3 to the k plus 1.
Okay.
7 to the k plus 1 minus 3 to the k plus 1 equals 7 times open parenthesis. 7 to the k minus 3 to the k close parenthesis plus 7 times 3 to the k minus 3 times 3 to the k,
Right.
which equals 7 times open parenthesis, 7 to the k minus 3 to the k close parenthesis, plus open parenthesis 7 minus 3 close parenthesis times 3 to the k, which equals 7 times open parenthesis 7 to the k minus 3 to the k close parenthesis plus 4 times 3 to the k.
Right.
From our inductive hypothesis,
Yeah.
we know that 7 to the k minus 3 to the k equals 4d.
Right.
Substituting this in, we've got 7 times 4d plus 4 times 3 to the k,
Okay.
which is 28d plus 4 times 3 to the k,
Yeah.
which is 4 times open parenthesis 7d plus 3 to the k, close parenthesis.
Okay.
Since d and k are integers,
Yeah.
open parenthesis 7d plus 3 to the k, close parenthesis, is also an integer. Therefore, we have shown that 7 to the k plus 1 minus 3 to the k plus 1 is 4 multiplied by some integer.
Okay.
Open parenthesis 7d plus 3 to the k, close parenthesis,
Yeah.
which means it's divisible by 4.
Right.
Thus, p of k plus 1 is true whenever p of k is true.
Okay.
By mathematical induction,
Yeah.
7 to the n minus 3 to the n is divisible by 4
Right.
for all positive integers n.
Okay.
The key insight here was the algebraic trick of adding and subtracting a term,
Yeah.
open parenthesis 7 times 3 to the k, close parenthesis,
Right.
to reveal the inductive hypothesis.
That was another insightful example.
Thank you.
Showcasing how we can leverage the inductive hypothesis in clever ways.
Yeah.
Especially with divisibility proofs.
Uh-huh.
Okay, the next one is Bernoulli's inequality.
Okay.
Open parenthesis 1 plus x, close parenthesis, to the n is greater than or equal to 1 plus n times x for x greater than -1.
Right.
So this one involves an inequality, but it also has a variable.
Right. So let p of n be the statement, open parenthesis, 1 plus x, close parenthesis, to the n, is greater than or equal to 1 plus n times x for x greater than -1.
Okay.
The condition x greater than -1 is important because it ensures that 1 plus x is positive for many of our manipulations.
Okay.
Basic step for n equals 1.
Yeah.
The inequality becomes open parenthesis 1 plus x, close parenthesis, to the 1 is greater than or equal to 1 plus 1 times x,
Okay.
which simplifies to 1 plus x is greater than or equal to 1 plus x.
Right.
This is clearly true for all values of x, including x greater than -1.
Yeah.
So p of 1 holds inductive step. We assume p of k is true for some positive integer k,
Okay.
meaning open parenthesis 1 plus x, close parenthesis, to the k is greater than or equal to 1 plus k times x for x greater than -1.
Right.
We want to prove p of k plus 1, open parenthesis 1 plus x, close parenthesis, to the k plus 1 is greater than or equal to 1, plus open parenthesis k plus 1 close parenthesis x for x greater than -1.
Okay.
So since we know that x is greater than -1,
Yeah.
1 plus x is a positive quantity. Therefore, we can multiply both sides of our inductive hypothesis by 1 plus x
So.
without changing the direction of the inequality.
Right.
So open parenthesis 1 plus x, close parenthesis, to the k times open parenthesis 1 plus x, close parenthesis,
Yeah.
is greater than or equal to 1 plus kx times open parenthesis 1 plus x, close parenthesis.
Right.
So open parenthesis 1 plus x, close parenthesis, to the k plus 1
Right.
is greater than or equal to 1 plus x plus kx squared.
Okay.
Our goal is to show that this resulting expression is greater than or equal to 1 plus open parenthesis k plus 1 close parenthesis times x.
Okay.
So let's compare the right-hand side. We have 1 plus x plus kx plus kx plus k squared. With the right-hand side, we want
Okay.
1 plus x plus kx.
Right.
The only difference is the term kx squared.
Right.
Now consider the fact that k is a positive integer.
Okay.
So k is greater than or equal to 1,
Uh-huh.
and x squared is always non-negative.
Right.
X squared is greater than or equal to 0.
Yeah.
Therefore, the product kx squared must also be greater than or equal to 0.
Okay.
So kx squared is greater than or equal to 0.
Uh-huh.
This means